Lesson 11.5 is about sums of both arithmetic and geometric series. So we're going to be finding the sum of those finite series. So there's two equations that you need to know. So for an arithmetic sequence, the sum of the first n terms is given by what you see here. So where n, again, is the number of term, t1 would be the first term, Tn would be that specific number term divided by 2. Now for geometric series, same idea here. T1 is the first term. R is that common ratio always to the n power n is the number term. And then in this equation, R can't be equal to 1 because we would have a divided by 0 error. So for example 1, it says find the sum of the first 13 terms. Just so you know, another way of saying that the book might use these directions is find the 13th partial sum. Partial meaning we're finding a finite number of the terms. Like the series could go on forever, but we're just finding part of it up until the 13th term. So here we go. The first thing we want to do is determine, is this an arithmetic or geometric series? In this case, this is arithmetic because I can see that my common difference is 4. I'm adding 4 between each term. So the formula that I'm going to use that was on the first slide is Sn, meaning the sum up until the nth number term, is n times t1 plus tn all over 2. So we're finding the 13th partial sum, so my n is 13. I'll plug that in here, and I'll do this kind of in an extra step here and here. And so then the last thing to do is to plug in what is the first term, what is the first term and what is the 13th term. Well, the first term is going to be easy to find. You're going to be able to read it straight off, so that's T1. The 13th term is going to take a little bit more work. Now, remember, this is something that you learned earlier in this chapter, is how to find a specific number term. That formula for an arithmetic sequence is Tn equals T1 plus n minus 1d. So if we're finding the 13th term, we're taking the first term, which is 3, plus 13 minus 1 times our common difference of 4, which we already determined. So that is going to be equal to 51, and that's what I'm going to put right here. So putting that all together, we have 13 times 3 plus 51 all over 2. So the 13th partial sum, or if we added up all the first 13 terms, is 351. Okay, next example, find the ninth partial sum. So again, we want to determine, is this arithmetic or geometric? Here again, we have an arithmetic sequence, and our common difference is equal to -2. So we're trying to solve S9, because this is the ninth partial sum. So we're going to take 9, which is our n, times T1 plus T9, it's a 9, sorry, over 2. Now T1 we can get just by reading off, but T9 takes a little bit more work. So what we're going to need for that is the same formula from earlier in the chapter. T9 equals T1 plus n minus 1 times d. So that's going to be T1 is 10 plus 9 minus 1 times our common difference of -2. So that's -6. So putting that all together, the ninth partial sum is 9 times 10 minus 6 over 2, or 18. Now you may be thinking, I could have just come up with the first 9 terms and added them all up. Totally true. 9's not that much. This formula is particularly nice for, what if I said add up the first 100 terms? Well, you're not going to do that by hand. You're definitely going to go straight to the formula. All right, example 3 says find the sum of this arithmetic series. And again, this is the 100th sum. So now we definitely want to be using this formula because we don't want to have to add up all of the terms individually. So this is given to us in a little bit different format too. It's not that we have, the first 3 terms and then we're trying to find the rest of it. We have some specific information here. We have the n, which is the 100th, the number term we're looking for, the number sum, and then the 100th term and the first term. So actually, it looks a little different, but it's easier. So we're trying to find the sum up to the 100th term. So this is arithmetic, so using that same formula, it's 100 times T1 plus T100. So that's just given to us, T1, T100 over 2. End of story. So the sum is equal to 11,600. Okay, find the sum of the first 10 terms. So this is example number 4. So we ask ourselves, is this arithmetic, geometric? In this case, it's geometric. You can see to get from one term to the next, I'm multiplying by 2. So the formula, is the sum up till the nth term is T1 times 1 minus r raised to the n all over 1 minus r. So let's plug in what we know. So we're trying to find the 10th term. So I'm going to make my n 10 equals T1, which is 2, times 1 minus my r is 2 to the n, which was 10, all over 1 minus 2. So if we do that math, we get 2,046 as the sum of the first 10 terms if we added them all up. Okay, same question here, example 5. In this case, we have another geometric series, and our ratio this time is -1/2. That's what we're multiplying by to get from one term to the next. So if we're going to find the 10th partial sum, we're going to take T1, multiply that by 1 minus r raised to the n all over 1 minus r. So we have some minus and negative there, so we can make that positive. In this case, we're going to get 66.602 for our 10th partial sum. Okay, here's the same question, and this is in summation notation. So this is asking the same thing. This is going to be key for the test, is knowing that this summation sign is asking you to find the sum up until 50. So that Greek letter sigma means the same thing. It means add starting at 1 up to 50. Okay, so we were told that this was an arithmetic sequence, so we know that the formula is going to be n times T1 plus T50 over 2. So in that case, this n right here is 50 as well. So let me put that in. So S50 equals 50 times T1 is going to be the first term. So we're going to need to solve for that really quickly using this formula here. So T1 is what we're going to get when we plug in 1 for our j. So that's 3 times 1 plus 2. T50 is what we would get if we plug in 50 for our j. So that's 3 times 50 plus 2. So using that formula is what allows us to plug in both of the values T1 and T50. So T1 is 5 and T50 is 152. So putting that all together, if we added up the first 50 terms, we'd get 3,925. Okay, let's do some word problems. So this is example number 7. It says a seating section in the corner of a basketball arena has 4 seats in the first row, 6 seats in the second row, 8 seats in the third row, and so on, until there are 28 seats in the top row. So the question is, how many seats are there in the entire section? So let's look at what's happening. Let's think of this as a series, which it is, because we have 4 seats in the first row. We're trying to figure out the total number of seats. So we'd add that with the seats in the second row, and then we'd add that with the seats in the third row, and then we would keep adding those seats. Now we know that it's going to end with 28 seats in the top row. So this is our first term, n is 1. This is our second term, or our second row of seating. This is our third. And we can also tell that this is an arithmetic series. We can see that there's a common difference of 2 between the terms. So what we're really trying to figure out is a sum, but the question is sum up until what, right? So it's, our Sn equals n times T1 plus Tn all over 2. So remember though, this is our Tn. This is the term in the nth position, but we don't know what n is. We don't know what row that is. It just said the top row. So the first thing we need to do is figure out, well, what is the top row? So for that we say, okay, we know that the nth term, so Tn, is 28. And we know that it's arithmetic. So let's use this formula to figure out what our n is. So Tn is 28. That's the last number of seats in the last row. So the term in the nth position. Then T1 is 4, n minus 1, and our d we said was 2. So now I can solve this. 28 equals 4 plus 2n minus 2, and then I get 2n equals 26, or n is 13. Ooh. So it's supposed to be an n. There we go. So this is the 13th term. So what we're really trying to do is sum everything up until that 13th term, or that 13th row. So that helps. Now we can plug everything else into this formula. We know the first term is 4. We know the nth term is 28. And we can learn that there are 208 total seats. Make sure for a word problem, you do include those units. Okay, last example here, another word problem. It says the Emperor of China was so excited about the game of chess that he offered an inventor one wish. The inventor replied that he wanted 1 grain of rice on the first square of the chessboard, 2 grains on the second square, 4 on the third, and so on through all 64 squares. The unwitting emperor immediately agrees to the seemingly modest request. How much rice will the inventor get? Okay, let's figure out what's happening here. So in the first square, we're going to get 1 grain of rice. We're going to add that with the 2 grains of rice we get on the second square. We'll add that with the 4 grains of rice we'll get on the next square. And we can already see here that we have a geometric sequence, or geometric series, because we're adding them up, with a common ratio of 2. So if we think about, well, what would happen if we added up all these terms up until the 64th term? Let's use our formula. So remember, it's T1, 1 minus r to the n, all over 1 minus r. So the first term is 1. 1 minus r is 2 to the 64th, all over 1 minus r. So if I put that together, put it in my calculator, we're going to get 1 point, I'll round to 84, times 10 to the 19th grains of rice. We'll talk about in class what that means. Think about if you said the same thing with like pennies. Think about how much money you would actually have. We'll talk about that in class. But that's the basics for that word problem. You can see Schoology for homework. This is lesson 11.5.